Math 1343, Week 10, Video 3, Describing Variability. Prior to showing you the formulas that are going to help us calculate our test statistic in an ANOVA, we need to know just exactly what it is we're looking for. And by the way, why are we using variance and variability to test means instead of using the actual means themselves? Well, the truth is we're going to use a little bit of both. But I want to give you a visual of what we're going to be looking for. Keep in mind that we're comparing multiple samples from multiple populations, and we're trying to use those to gauge whether or not the population means could be the same. So, when gauging samples in a data set to determine if population means might be equal, a visual representation of the data will often be helpful. The stronger the overlap in the visual representations, the better chance the population means might be equal. We'll be looking for two types of variability, but I'll explain what those are in just a second. But first, I want to go to my spreadsheet for a moment and kind of show you what we're talking about. For example, what you see here are some vertical dot plots for the data set that we had earlier in the previous video about the number of hits acquired from each team in the Major League season 2019 based on the position in the batting order. In other words, all this data got turned into these pictures. Without rehashing exactly what a box plot is, let's just zoom in on the first one, which is for first batting position, which is indicated by the legend down here. Just a quick reminder of how box plots are created. The three lines in the box plot represent the quartiles. So the line across the middle is the median of the data set. The lower line and the upper line are the first and third quartiles, the numbers that separate the bottom 25% and top 25% of the data set. Now, if you're accustomed to seeing box plots go horizontally, instead of going left to right, which I have to be careful because of the way I'm facing the camera, they're going from bottom to top. The whiskers go to the highest point and lowest point. That's not considered an outlier. And if there happens to be an outlier, it's usually represented by a dot. But the question we're trying to answer in terms of this number of hits acquired from each position in the batting order is the mean the same? Well, based on these samples, notice that there's pretty strong overlap, horizontally speaking. For example, if we were to go across here, we would hit 3 of these boxes. Across here, we would hit some of them and some of the whiskers. The only guy that really stands out is this guy over here. But visually speaking, if we're trying to address whether or not multiple population means might be equal by looking at samples from each population, then visually, the more overlap there is between all of the pictures, the stronger the evidence there is that the population means might be equal. But I mentioned that there are two types of variability that we're going to be looking for. It's easier to see than it is to put into words. One type of variability we're going to be looking for in our pictures is variability between groups. Think of each box in the box plot representing a group. Variability between groups is when a lack of overlap of samples is based on where the samples are located relative to each other. You can think about it about where their means are located on a number line, and not necessarily the sample's variances or standard deviations. Visually speaking, when we talk about the sample's variance / standard deviation, what we're really talking about is the width of those boxes, loosely speaking. And when we talk about the location of their means, what we're loosely talking about is the center, not really the center, but some number in the middle, a measure of central tendency representing each box. So if we have boxes that don't overlap, not necessarily because of how wide they are, but because of where they're positioned relative to each other, we would call that variability between groups. Now, variability within groups is like the same thing except completely backwards. That's when a lack of overlap of samples is based on their variances or standard deviations. In other words, how wide the boxes are, and not necessarily the locations of their means. In other words, where they're centered. The easiest way to keep these sorted out is to show you a visual and then give you a gimmick. so let's go back to the Word document, the Excel document for a second, and we'll go to the next page. Now, these two dot plots from two different groups of samples were created from some fictitious data. They don't have anything to do with the baseball data that I shared earlier. But two different people were gathering samples from three populations to attempt to answer the question, are your population means possibly equal, or could some of them be different? The first person gathered data, and these are their box plots, pretty wide. Second person gathered data from the same populations, but these are their box plots, fairly skinny. Now, it may not be evident here, and maybe I can make that more evident by shifting one of these up and the other one down. Move this one down. What I'm trying to do is line up the horizontal values. Here's 25 right here, and there's 25 right here. And now it may be a little bit more evident that if you look at the X's in the middle of each of these box plots, they represent the means. And if you'll notice, the means for each sample from corresponding populations are the same. The mean here is about 25, as is this one. Actually, it's exactly 25. For the orange one, the mean is 20, as is this one. And for the blue one, the mean is 15, as is this one. I chose the data to make that happen. But of these two data sets, data set 1 and data set 2, person 1 gathered data, this is their picture. Person 2 gathered data, this is their picture. Which of these data sets provides stronger evidence that the population means might be the same? That's equivalent to saying which of these data sets have a stronger overlap in their pictures. And I think it's fairly obvious that it's data set 1. The orange and gray boxes clearly overlap here, the blue and orange is here. And the gray and blue boxes don't quite overlap, but their whiskers do kind of run into each other. But if you look at data set 2, there's absolutely zero overlap. But what do we blame the overlap on? Are we blaming it on the location of the boxes, aka their means, or their centers, if you will? Well, we can't really do that because the centers are exactly the same. We're blaming the discrepancy on the fact that even though the positions of the boxes are the same relative to their centers, the boxes on the left have a much smaller variability, a much smaller variance or standard deviation. All three of those words would work here. And you can tell because they're all thinner. So if we were to pick one of these as stronger evidence of equal means, or flip that, which of these provides stronger evidence of different means, we would choose data set 2 to say it provides stronger evidence for different means, or we would choose data set 1 to say it provides stronger evidence of equal means. But the reason we would say that is variability within groups. We would say variability within groups. We would say variability within groups. Where is my heroes? We would say variability within groups, the blue one, because the lack of overlap is based on the variance in standard deviation. In other words, how wide each box is, and not necessarily the locations of their means. Now, let's go back and look at a different pair. Back and look at a different pair. Kind of gave it away with the names of the tabs down here. All right, so here we have the same scenario where two people, I didn't change these, two people took 3 samples from 3 different populations and got 2 different data sets, data set 1 and data set 2. And in case you're wondering, yes, the first data set is identical to the previous page. And I want to do one more thing. I want to line these up so that the horizontal numbers are lined up with each other. So, oh, I gotta go, that's it. So 35 is here and 35 is there, 30 and 30, 25 and 25. All right, so we have a little bit more consistency on the horizontal scale there. You can kind of see the numbers hiding back there. All right, so if we were to look at these and ask the question, which of these data sets provide stronger evidence that the population means might be equal, or vice versa, which one provides stronger evidence that the population means might be different, we're still asking which one has stronger overlap. Well, the stronger overlap is still data set 1. Because if you notice, there's less overlap with data set 2. But what's the reason? And we blame it on the fact that data set 2 has a smaller variability within each group, like we did over here. Well, no, we can't. If you were to compare them, you would see that these boxes are actually the same size. I'm not going to drag and drop it, but all I did is add the same amount to each data point, which just moved the box up, or in the case of the blue one, moved it down a little bit. But the boxes are actually identical. The scaling's a little bit off because you can tell that these lines are wider apart than the other ones. See if I can fix that. Trying to line these up and everything nice and pretty, and didn't get it exactly the way I wanted. But we can still kind of tell, even if you can forgive the fact that the scaling on the y-axis is a little bit different on the two, that data set 2 has less overlap, but we can't blame it on how thin the boxes are. We can blame it, however, on their locations, for their means, if you will. For example, if you look in data set 1, the 3 means are still 15, right there, 15, 20, and 25. But where are the means now? 10, 20, and 30. And again, if you trust me, the boxes are identical, but data set 2 has less overlap based on where the boxes are located. So we can't blame it on how thin they are, but we can blame it on how much variability we have between corresponding groups. For example, the variability from this blue box to that blue box, or specifically the variability between their means. And think of it that way, the variability between these means, between these 3 x's, is greater than over here. In this one, the variability between the means, and therefore between the groups, is exactly the same, because the means were in the exact same locations. But here, these means are further apart, so we have a variability between these groups to blame for the lack of overlap. So in terms of what we were talking about before, for the second picture, it was, we choose, let's go back for a second. For the second data set, we would say that it provides stronger evidence of different population means, less overlap, due to variability between groups. Between these groups over here, they vary more than the groups vary over here. That's all this was saying over here. That variability between groups is when a lack of overlap of samples is based on where the samples are located relative to each other. In other words, the locations of their means, and not necessarily the sample variances and standard deviations. In other words, the widths of the samples. So when you are asked to choose one data set over another to provide either stronger evidence that the means are equal or stronger evidence that the means are different, you choose the one with less overlap. But when I ask you why did you choose that one? Or what is causing the lesser overlap? The correct response will be to say either variability between groups or variability within groups. Now, I'll admit, when I was first preparing to teach this many years ago, I was struggling to find a good way to remember that on this one, we choose data set 2, providing stronger evidence of different means due to variability between groups. But on this one, we choose data set 2 that provides stronger evidence of different means because of variability within groups. And I was looking for a gimmicky way to remember to say, this one we choose because of within groups, variability within groups, and this one we choose data set 2 because of variability between groups. And I wish I could remember the student's name, but they came up with a brilliant gimmick that I use to this day. If you choose a data set based on how thin it is, in other words, if you're blaming the lack of overlap based on how thin the boxes are, not their locations, but how thin they are, thin, it's variability within groups. In other words, the word within contains the word thin. Highlight it. Highlight is what I want to do. There we go. There it is. The word within contains the word thin. Meaning, if you pick a data set, if the reason you pick a data set as evidence that means are different is because the boxes are thinner, then you say variability within groups. Otherwise, you say variability between groups. Let's take a look at one more. I don't have something nifty created in Excel. I'm just going to draw this one, but it'll be pretty quick. Because there are multiple ways to represent data things as plots. Dot plots. We could even use rough bell curve sketches. So for example, let's say that we had data set 1 that was comparing, let's just say 2 groups, although typically for analysis of variance, you're testing 3 or more populations, because if you're only testing 2 populations, you just test the difference in means like we did when we reviewed stats 1. But let's say in data set 1, we gather some data and we make some dot plots on a number line, and they kind of form these 2 bell curves. Bell curve 1 and bell curve 2. Then on data set 2, somebody gathers samples from the same populations and they get the following. Data set 1 bell curve, data set 2 bell curve. Now, both bell curves overlap. On the top, they overlap about here. On the bottom, they overlap about there. But if I were to ask you, which of these provides stronger evidence that the population means are different, which one would it be, data set 1 or data set 2? Well, the stronger the overlap, the stronger the evidence that the means are equal. The less the overlap, the less the evidence the means are equal. So the one that provides stronger evidence that the population means are actually different would be data set 2. There is less overlap. But would we say we chose that one based on variability between groups or variability within groups? Look at where the centers of these are. The centers are pretty much in the exact same place. So we're not blaming the lack of overlap based on the location of the bell curves. We're blaming the lack of overlap based on the thinness of the bell curves in the second data set. And so if we were to answer why is it data set 2, we would say variability, do not spell that correctly, variability within groups. I'm saying within because I chose data set 2 because they're thinner. If I chose because of the locations and not the thinness, then I would have said variability between groups. It's actually not a difficult thing to do. I'll give you 2 pictures and which one provides stronger evidence that the population means are different. The answer is whichever picture has less overlap amongst its components. And as for the reason, if the reason there's less overlap is the location, say variability between groups. But if it's because of the thinness, then you say variability within groups. What if it's both of them? Well, I'm not going to ask you that, but it is possible both, in which case we could cite both. All right, I hope that made a little bit of sense. It's a little easier when we're having a dialogue instead of a monologue, but such are the slings and arrows of pre-recorded lectures.